Here's a graph that could represent some sort of communication network between 5 different vertices. It could be a local area network with nodes, or it could possibly be 5 cities and we're looking at roads between them. Maybe 5 cities, and this is the historical genesis of this idea of practical applications of graphs. Goes back to the 1930s in Czechoslovakia, where they were looking at towns and building high-powered electrical transmission lines between them, and deciding what's the cheapest way of connecting all of those cities with each other. So the idea is that we've got various vertices, and you can see there's a lot of redundancy in this if you're just thinking about it as a connection, as a system of communications. So if you want to communicate between A and D, there are lots of different ways. There's a direct communication, or you could go via C, or perhaps via B and then C, or maybe even ABC, ACB, DE, very indirect. And there's a lot of redundancy. There's a lot of different paths between any pair of vertices. Then you start to think, well, maybe we could build these sorts of things with less redundancy. I mean, sometimes redundancy is good if this is a communications network and an edge disappears, then, or a link disappears, then there are still different ways to get there. So if AE disappears, the direct link disappears, there's still a way of communicating, but via C. And then if the link from A to C disappears, well, there's still a way of going from A to B to D to E. So if these two disappear or break down, there's still communication possible. But as I said, this leads into an idea of, is there a way of building the network, in a sense, with the least amount or zero redundancy? So for example, you might build a network that looks like this. Let's see there. Let's connect those two, and let's connect that. And you can see that every vertex is still connected or connected to every other vertex, in the sense you can still find a path there, but there's absolutely no redundancy involved. So if C to E disappears, then the network is broken and you simply won't be able to communicate from A to either B or C. So if this one goes, A and B and C are isolated from each other. This sort of thing is called a spanning tree. And you can see that this idea of trees having only one path between any pair of vertices means that there's absolutely no redundancy. Here there are lots of paths between vertices, so lots of redundancy. In a tree, there is only one path between each pair of vertices. This idea of a spanning tree simply means that we take the original graph, we find a tree structure within it, but it uses every vertex of the original graph. So we've got A, B, C, D, E, and here we've got A, B, C, D, and E. And there are lots of different spanning trees. Here's another one. So again, no redundancy. Every link is vital. Breaking any link will mean that there'll be some vertices that are not able to communicate with other vertices. So once we get that idea of a minimum spanning tree and the idea of building things we start to say, well, if we're going to build them, maybe things cost to build. So this is where we get this idea of a weighted graph. So maybe D to E costs $11,000. So the idea is that we put a weight on each of the edges. And this one costs $6,000. This one costs $1,000. So $3,000. $3,000. I'm just talking thousands of dollars. $6,000. Let's say this one is $5,000, and finally this one is $7,000. So then you ask yourself, oh, how much does it cost to build a network which has the fewest edges, so the least amount of redundancy? If we look at the costs, I mean, for this one, 7,000 for that, 1,000 for that, 11 for that, and 5. So we talk about the total weight being 7 plus 11 plus 5 plus 1, which is equal to 18, 19, 24, I think. So maybe this costs $24,000. This one, on the other hand, 6 for that, 1 for that, 3 for that, and 5 for that. So this costs $6 plus 1 plus 3 plus 5 equals $15,000. Once you start putting weight on it and you think about what's the cheapest way of doing things, and so we can ask ourselves, well, what is the minimum? And this idea leads on to a minimum spanning tree. So what's the spanning tree of least weight? So we want to find spanning tree of least total weight. Now clearly this one is not, but this one, can we do any better? Is there another tree in there that is cheaper to build? And the answer is, well, we'll see next time when we work out an algorithm. Now, with a very small graph like this, it's probably fairly easy just to try and look at everything and just observe and see that this is probably going to be pretty close to it. There's probably not much else that you can do. And in fact, it does turn out that this is the cheapest. But if you had a bigger structure, bigger tree to begin with, what would be the method to discover the minimum spanning tree? So, weighted graphs are simply graphs with weights on them that represent a cost to build. Spanning trees, a tree that's within the graph that covers every vertex, and this idea of minimum redundancy. Now the trade-off is that having redundancy in a network means that links can drop out and you can still communicate. No redundancy means that links can drop out and all of a sudden the whole network is broken. Then once we've got weights, we can think of, what is the minimum weight possible amongst all the different spanning trees. So next time we'll do a couple of algorithms